All right. Um, so we have, so far we've studied several different kinds of functions. So we spend a lot of time talking about polynomials and rational functions. And just a little kind of, I guess, not a little lesson about math, not just on math. Polynomials and rational functions are called algebraic functions. And that's the reason they're called algebraic functions is because there's a split or a subset. So we know about real numbers and rational numbers. There's a subset of the real numbers called algebraic numbers. And we have also studied trig functions. And now we're going to study exponential functions. And when I'm talking about the functions, the functions and their inverses, these trig and exponential functions are called transcendental functions. And the reason they're called transcendental functions is because the solutions to trig and exponential functions can be what we call transcendental numbers. So for example, we know when we solve trig equations, we can get pi as a solution, or pi over 2. But that number can never be the solution. Pi over 2 is never the solution of a polynomial, the way we define a polynomial. So there's kind of a split between the two kinds of numbers, and there's a split between the kinds of functions that are solutions to those kinds of equations. And with the exponential functions, we'll have all of these are the main families of functions that you study in math. There are other kinds, but these are the main families of functions. So we're kind of completing our fundamental study of functions in this section. But for today, we're going to talk about exponential functions. Exponential functions are really nice functions. They're about the simplest function that we can have, just about. Exponential function, it looks like this. F of x equals a to the x. And just to contrast it with a polynomial, with a polynomial we were raising x to powers. Now we're using x, we're using our variable as the power. All right, we call a is the base of our exponential function. And we want a, for what we're doing, a is going to be positive. And a is not equal to 1. Because if a is equal to 1, it's not a very interesting function, because it's just 1 all the time. And x is any real number. So very simple to write a function. They behave in really nice ways. And they're important to study because they model a lot of, we use them to model cell growth, population growth, radioactivity, compound interest. We'll talk about that today. So they model a lot of real world phenomenon. All right, so we're good with the idea of an exponential function. Okay, let's talk about our properties, some properties. Then one of the nice things about exponential functions is all of them share the same properties. We don't have to say, well, if this, then it does this, if that, then it does that. They're all the same. So we have f of x equals a to the x. Our domain is all real numbers. We could also write it in interval notation, negative infinity to infinity. So we can put any value of x in there. Nothing's going to give us a problem. The range. The range is real numbers greater than 0. Because if our base is positive, we can never get a negative number. So we could also write that as 0 to infinity. And we have a curvy bracket because it doesn't, or curved bracket because it doesn't equal 0. The Y-intercept. For any unshifted exponential function, doesn't matter what the base is 0, 1. And that's because any number to the 0 power is 1. Doesn't matter what the number is. So any unshifted exponential function is going to go through the point 0, 1, no matter what. Since the range is real numbers greater than 0, it has a horizontal asymptote. At y equals 0. So the x-axis is a horizontal asymptote. Every unshifted exponential function will have a horizontal asymptote at y equals 0. It's increasing. Means it always goes uphill if a is positive. Or sorry, a is greater than 1. And f of x is decreasing if a is a fraction between 0 and 1. It means it always goes downhill. So no matter what. It's a very simple set of properties that all exponential functions have. We don't have to worry about going up and down, up and up, down, none of that stuff. All right, questions on our properties? Let's talk about the graphs. Another nice thing about exponential functions is the graph of any exponential function is more or less the same as a graph of any other exponential function. There's not much difference. We don't have to worry about the multiplicity and all that kind of stuff through the x-axis, touching the x-axis. All the graphs look basically the same. So I'm going to show that by doing a couple of examples. F of x equals 2 to the x. We'll graph that one, and then we'll graph a sibling of that one. Well, we know that it's going to have a horizontal asymptote at y equals 0. And we're just going to plug in some points. So f of, do it over here, f of negative 2 is 2 to the negative 2. And I can rewrite 2 to the negative 2 as 1 over 2 squared. So it's 1/4. So over here at 2, we get a point at 1/4. F of negative 1 is 2 to the minus 1, which is 1/2. Going to go down here. F of 0 is 2 to the 0. It's 1. Our exponential function is always going to go through that point if it's not shifted. F of 1 is 2 to the 1, which is 2. And f of 2 is 2 squared, which is 4. So that goes up a little steeper. So our function looks the graph of our function looks like that. And as x approaches negative infinity, it shouldn't go back, it should go down towards the asymptote. As x approaches negative infinity, our function gets closer and closer and closer to 0. Never actually gets to 0, but it gets as close as we want. Every unshifted exponential function where our basis is greater than 1 is going to look more or less like that. Let's do another one. The sibling of this one. F of x equals 2 to the negative x. Now before we graph here, I want to write this in a couple of different ways. 2 to the negative x is the same as 1 over 2 to the x, which is the same as 1/2 to the x. All three of these things mean the same thing. So it's going to be important to be able to recognize these three all as the same thing. All right, so let's graph this one. And we're going to go, we'll do our points in reverse order. F of 2 is 2 to the negative 2, which is 1 over 2 to the 2, which is the same as 1 over 2 square, 1/2 squared, which is 1/4. So here at x equals 2, I get a point at 1/4. We know we have a horizontal asymptote. Let me put that in. At y equals 0. F of 1 equals 2 to the negative 1, which is 1/2. So it goes up a little bit more. F of 0 is 2 to the negative 0, which is 1. Always goes through the point 0, 1. It's not shifted. F of negative 1 is 2 to the negative 1, which is 2. Do we see what's happening here? F of negative 2 to the negative 2, which is 4. So my function is going to look like that. How are those two related? They're flipped. They're reflected across the y-axis. For what we've done with transforming functions before, what happens when we change the x to the negative x? It's a reflection over the y-axis. And this function increasing, this is greater than 1. This one's decreasing because this is less than 1. All graphs of exponential functions are going to look more or less like that. Let's talk about shifting. Shifting graphs. So really all I'm going to say about this is exponential functions shift like any other graph. Or I'm going to say transform. So all the rules, all the things that you know about shifting functions is the same for exponential functions. There's nothing different. What that means is the intercept and the asymptote shift with the function. So if the function shifts up 1, your asymptote shifts up 1. Your intercept shifts up 1. If your function reflects over the x-axis, the intercept reflexes over the x-axis. If you go left, right, left 3, up 2, your intercept goes left 3, up 2. Now going left or right doesn't affect the asymptote, but going up would. So you shift the intercept and the asymptote with the function. So for example, what if our parent function is y equals 4 to the x? I just want to describe what this function does. Y equals 4 to the x plus 2. So what happens when we add or subtract, when we add something inside the function? Yeah, this is going to be left 2. So our asymptote shifting left or right doesn't matter. But our intercept that's at 0, 1 would shift left 2. So it'd be at 0, negative 2. Sorry, negative 2, 0, 1? Negative 2, 1. Sorry. Yes?
So, but that wouldn't happen if the plus 2 is after the 4.
No. So let's look at one of those. Y equals 4x plus 2 plus 3. So what would happen with this one? Left 2, up 3. So our intercept would shift over to negative 2. Sorry, negative 2, 1. And then go up 3. So it'd be a negative 2, 4. Our asymptote would go up 3. So we could use that to sketch our graph. How about y equals negative 4 to the x? Yeah, that's going to reflect over the x. So our intercept that's at 0, 1 would reflect down and be at 0, negative 1. And how about y equals, we just talked about this, 4 to the minus x? That's going to reflect over the y. And so our intercept and our asymptote aren't going to change because that doesn't change when we reflect over the y, but our function is going to be reversed, essentially. So all these rules that we're familiar with apply to exponential functions as well. Now I would say that the graphing part is students' least favorite part of Chapter 3. Graphing is students' least favorite thing all the time. Did I tell you they asked me to teach another class? I said, yeah, I'll teach pre-calc, I'll teach geometry, I'll teach Calc 3, but at graphing I draw the line. All right, one important application of exponential functions, compound interest. So what we mean by compound interest is instead of just earning a set interest rate on our investment, we earn interest on our investment every certain amount of time. And then whatever we earn interest then on what we had originally plus what we had interest on. So we're earning interest on our interest. That's what compound interest means. So I'm going to say here A sub n is the amount after n pay periods. And P is the principal. That's how much we start with. And X is the interest rate. Usually our interest rate is going to be something % per year, usually. So what we're going to do is develop a formula for our compound interest for compound interest. And we're going to use the process that we did in Chapter 8 when we talked about sequences and series. So our original amount after 0 pay periods is just our principal. A sub 1 after 1 pay period is going to be the principal plus the interest that we earn, P times X. So we earn interest on this and we add it to whatever we had. Well, I can factor this. I can factor out the P. This is going to be P times 1 plus X. After 2 pay periods, we have what we had here plus the interest we earn on this. Well, this time I can factor a P times 1 plus X out. I have a common term of P times 1 plus X. Well, this is P times 1 plus X times 1. And here we have an X. Well, that's P times 1 plus X squared. After 3 pay periods, we have this much, P times 1 plus X squared, plus the interest we earn on this, P times 1 plus X squared times X. Well, now I can factor the P times 1 plus X squared. Sorry, this should be X squared out here. And when I factor that P times 1 plus X squared out of this, I get a 1. And when I factor it out of this, I get an X. Well, that's P times 1 plus X to the third. Do we see the pattern? A sub n is P times 1 plus X to the n. So compound interest is exponential. The more pay periods we have, the pay period is our exponent. So our money grows exponentially relative to our pay periods. All right. So what we're going to do, usually we have an interest rate, a yearly interest rate, 5% per year or something, and we get our pay periods are a certain number of times per year. So we might get paid 12 times a year or 4 times a year, something like that. So we want to adapt this formula to work in that situation. So I'm going to write down the formula. This is to show that our formula is exponential. So we're going to adapt it to how it's really used. So in this case, we're going to say that A equals the amount after t years. So we're going to measure our time in years. P is the principal. R, in this case, is the annual interest rate. So 12% per year, 7% per year, something like that. And N equals the number of pay periods per year. So our formula adapted for this, which is the more common model, is our amount is the principal times 1 plus R over N to the NT power. All right, so I want to do an example with compound interest, and that's going to lead us into a special form of compound interest. So let's say we have $5,000. And we get paid, we earn 6% annually. We want to find how much after 10 years if we compound, and we're going to do several different versions just to compare. Compounded annually. So how many pay periods per year if we compound annually? 1. So here N equals 1. So our amount is 5,000. 1 plus our interest rate, 0.06, over 1. And we do 1 times 10. And you can plug it into your calculator like this. I would put, doesn't matter here, but in general I'd put some parentheses around that division. When you calculate that out, you get 8954.24. So you have almost $9,000 after 10 years. Now we're going to compound quarterly. So how many pay periods per year now? 4. N equals 4. So we get our amount is 5,000. 1 plus 0.06 over 4. 4 times 10. We calculate that out, and we get 9070.09 cents. So a little bit more, not a whole lot, even though we're compounding 4 times more often. Monthly. N equals 12. So our amount is 5,000. 1 plus 0.06 over 12. 12 times 10 is our exponent. And in that case, we get 9096.98. Notice we keep going up, but not super fast. Daily. Compound means how often you're paid your interest. So for daily compounding, we get 5,000. 1 plus 0.06 over 365. 365 to the 10th power. And in that case, I get 9110.14. So a little bit more, even though we're compounding a lot more, often. We could keep going. If we compounded every hour, we could compound every minute, we could compound every second. Eventually, we're compounding what we call continuously. So we see that our interest rate, the amount that we get, grows, but not really fast. I'm going to take a little side note here and say that this quantity, 1 plus 1 over x to the x power. So that's essentially what we have here. That's what we had back here. 1 plus 1 over 1 plus x to the n power. So it's essentially that. As x approaches infinity, so as we keep compounding our interest more and more often, this approaches e. It's an irrational number similar to pi. The number e shows up in all kinds of math, all kinds of science. It originally was discovered having to do with compound interest. E is about 2.718. We just had, nobody made a big deal of it, we just had E Day, 2718, 2718. It's the 7th of February. Yeah, I was waiting for all of you to throw a party for E Day.
Was E-Day like during the weekend?
What's that?
Was it Saturday?
It was a Saturday?
Saturday.
Oh,
I never find it. Oh.
that's the day that they're supposed to have that big protest.
Oh, really?
Yep.
That's the only time it'll ever be E-Day.
So, if this formula, when we compound continuously, our continuous interest formula, when we're as soon as we compound again, our formula becomes our amount equals P e to the RT. Usually students remember PERT. So in this example, our amount would be 5,000 e to the 0.06 times 10. And when we calculate that out, we get 9110.59. So continuously compounded interest gets us just a little more than we got if we compounded daily. And in your calculator, to calculate this quantity, you would use a button. Your calculator has the button e to the x. This number e is going to be pretty important for what we do in this chapter. No, E-Day was a Wednesday.
It was the 17th of
No,
February.
7.
Oh, the 7th?
7.
Sorry, my bad. I was Wednesday.
That was a Wednesday. All right, questions?
Thanks, Alice.
Now another interesting side note. So E is an irrational number like pi. E is also a transcendental number. But there's a very famous formula in math. E to the I pi plus 1 equals 0. It's kind of magical that it works out like that. So the kind of the main constants in math, e, I, pi, 1, and 0.
Math is the strangest thing ever.
So it turns out this way. If you, those of you that are sophomores, if you take Calc 2-3 here, we do a lab where we actually come up with that equation.
You do labs with them?
Yeah.
I'm not doing Calc. I know you are.
We don't? No, it says 3.1.
Do we have homework?
Yeah.
But it doesn't say on the board.
Yeah, we have 3.1 homework.
I'm doing the Genesis chapter today.
I have to actually do homework today. It's a weekend. Stop writing.
I will.
No, now. That's so many.
These are really easy.
Do they have like an ABC?
81 through 84 without your calculator.
What are you doing? Definitely negative.
I was seeing if I could troll Caleb twice today.
I wrote it down too.
Caleb, I did that to someone in my first period class, and he said, "Wait, why?" Oh, I didn't stop this. I didn't stop this recording.